Hello there, and welcome to my channel. I'm so glad you found your way here tonight. Whether you've had one of those days that stretched on forever, or your mind is buzzing with thoughts that just won't settle, this video is made especially for you. Tonight, we're going to drift gently into one of the universe's most captivating mysteries, dark energy, the invisible force that's quietly stretching the very fabric of space itself. But before we begin this cosmic journey together, I'd love to know, where in the world are you listening from right now, and what time is it where you are? Are you tucked into bed with the curtains drawn, or perhaps sitting somewhere peaceful with a warm cup of tea as the evening settles around you? If you find these gentle explorations of the universe soothing or intriguing, I'd be incredibly grateful if you gave this video a like and maybe subscribed. It helps other curious souls find their way to this calm corner of science, and it means I can keep creating these soft adventures through the cosmos for all of us. Now, I do hope this journey isn't too fascinating that it keeps you awake, though if it does, at least you'll drift off knowing a bit more about the mysterious force that's shaping our entire universe. Not such a terrible trade, really. So settle in, let your breathing slow, and let's take a peaceful wander through the story of dark energy and why it might just be the strangest thing we've ever discovered. Dark energy sounds like something from a science fiction thriller, doesn't it? The name alone conjures images of shadowy forces and cosmic villains lurking in the depths of space. But the reality, while no less mysterious, is far more subtle and profound. Dark energy isn't dark because it's sinister or hidden in shadows. It's dark because it doesn't interact with light at all. We can't see it, we can't touch it, and we can't directly detect it with any instrument we've ever built. Yet this invisible presence makes up roughly 70% of everything that exists. Let that settle in for a moment. Nearly 3/4 of our universe consists of something we've never actually observed directly. It's a bit like discovering that most of your house is made of rooms you've never seen, filled with furniture you can't touch, all while you go about your daily life in the small visible portion you call home. So what exactly is this mysterious force? And how did we even discover something we can't see? The story begins not with dark energy itself, but with the realization that our universe has been keeping secrets from us. For most of human history, we assumed the cosmos was static, unchanging, eternal. The stars seemed fixed in their patterns, the galaxies appeared frozen in time, and space itself felt like an unchanging stage upon which the drama of existence played out. But in the early 20th century, astronomers began to notice something peculiar. When they looked at distant galaxies through their telescopes, the light from these cosmic islands appeared shifted toward the red end of the spectrum. This redshift, as it came to be known, was like a cosmic whisper telling us that these galaxies were moving away from us, and not just moving away slowly, but racing away at incredible speeds. At first, this discovery led to the realization that our universe was expanding, growing larger with each passing moment, like a balloon being gently inflated. This was revolutionary enough. Space itself wasn't a fixed stage, but a dynamic, growing entity. The implications were staggering and beautiful in their simplicity. But then, in the late 20th century, astronomers made an even more startling discovery. They were studying distant supernovae, those spectacular stellar explosions that can outshine entire galaxies for weeks or months. These cosmic lighthouses are remarkably consistent in their brightness, making them perfect measuring sticks for gauging distances across the universe. What they found defied all expectations. The universe wasn't just expanding, it was expanding faster and faster. The rate of expansion was accelerating, as if some invisible force was stretching space itself with ever-increasing vigor. It was like watching a balloon inflate, and then realizing that whoever was blowing it up was taking deeper and deeper breaths with each puff. This acceleration couldn't be explained by anything we knew about. Gravity, the force we understood best, should have been slowing the expansion down, not speeding it up. After all, every galaxy in the universe is gravitationally attracted to every other galaxy, so the collective pull should be putting on the brakes, not pressing the accelerator. Yet the evidence was undeniable. Something was overpowering gravity on the largest scales, something that filled all of space and pushed against the universe's tendency to slow down. Scientists needed a name for this mysterious influence, and so they called it dark energy. Not because it was evil or foreboding, but because it remained hidden from our direct observation, dark to all our instruments yet clearly present through its effects. The discovery of dark energy was like finding footprints in fresh snow, with no visible creature to have made them. The prints were clear, the evidence unmistakable, but the source remained tantalizingly invisible. And just as those mysterious footprints would reshape our understanding of what creatures might exist in our world, dark energy has fundamentally altered our view of the cosmos. To understand just how profound this discovery was, imagine you're sitting by a pond on a calm evening, watching ripples spread out from where a stone has been dropped. You expect the ripples to gradually slow down and fade away as they move outward. But instead, as you watch, the ripples start moving faster and faster, spreading with increasing speed across the water's surface. You'd be witnessing something that defies everything you thought you knew about how energy moves through space. That's essentially what astronomers discovered was happening to our universe. The expansion that began with the Big Bang wasn't gradually slowing down as everyone expected. Instead, it was speeding up, driven by this mysterious dark energy that permeates every corner of space. But here's what makes dark energy so peculiarly fascinating. It doesn't seem to dilute or weaken as space expands. Most forms of energy become less dense as the universe grows larger. If you have a box of gas and you make the box bigger, the gas becomes less dense, more spread out. But dark energy appears to maintain a constant density even as space itself stretches. As the universe doubles in size, the amount of dark energy doubles as well, as if it's being created out of nothing to fill the new space. This property gives dark energy its remarkable power. While matter and regular energy become increasingly diluted as the universe expands, dark energy maintains its strength, eventually becoming the dominant force shaping the cosmos. It's like a gentle but persistent pressure that never weakens, always pushing outward, always encouraging space to grow. The mathematics of dark energy are elegantly simple, even if the physics remains mysterious. Einstein's equations of general relativity, the same equations that describe how gravity warps space and time, also allow for this kind of repulsive force. In fact, Einstein himself briefly considered adding such a term to his equations, something he called the cosmological constant, before later abandoning the idea. Decades later, astronomers discovered that Einstein's abandoned concept might actually describe the dominant component of our universe. This cosmological constant, if that's indeed what dark energy is, represents the energy of empty space itself. Even in the most perfect vacuum, quantum mechanics tells us that space isn't truly empty. It's filled with quantum fields that fluctuate and dance at the smallest scales, creating a subtle background energy that fills every cubic centimeter of the universe. If this quantum energy has the right properties, it could manifest as the dark energy we observe. But there's a problem with this explanation, and it's a rather spectacular one. When physicists try to calculate how much energy empty space should contain based on our understanding of quantum mechanics, they get a number that's about 10 to the power of 120 times larger than what we actually observe. This isn't just a small discrepancy. It's possibly the worst prediction in the history of science, off by a factor so enormous that it boggles the mind. It's like trying to estimate the weight of a feather and getting a number larger than the mass of all the galaxies in the observable universe combined. Clearly, something fundamental is missing from our understanding, some piece of the puzzle that would explain why the quantum energy of space doesn't completely dominate the universe's evolution. This enormous discrepancy has led some scientists to wonder whether dark energy is something else entirely. Perhaps it's not the energy of empty space, but rather a new kind of field that fills the universe, something that changes slowly over time. This hypothetical field, sometimes called quintessence, after the fifth element of ancient philosophy, would be dynamic rather than constant, evolving as the universe ages. Other theories propose even more exotic possibilities. Maybe our understanding of gravity itself breaks down on the largest scales. Perhaps Einstein's equations, so successful at describing everything from falling apples to orbiting planets to the bending of light around massive stars, need modification when applied to the entire universe. These modified gravity theories attempt to explain the accelerating expansion without invoking a mysterious dark energy at all. Some physicists have even suggested that dark energy might be a sign that our universe is embedded in a higher dimensional space, with forces from these extra dimensions influencing the expansion we observe. Or perhaps we're seeing the effects of other universes, parallel cosmos that exist alongside our own and exert a subtle influence on our space's geometry. Each of these possibilities opens up profound questions about the nature of reality itself. If dark energy is real and represents the energy of empty space, then nothingness isn't actually nothing, but rather a dynamic, energy-filled medium that shapes the evolution of everything that exists. If it's a new field or a modification of gravity, then our most fundamental theories about how the universe works may need radical revision. What makes this mystery even more intriguing is how dark energy interacts, or rather, doesn't interact, with everything else. Unlike the dark matter that holds galaxies together through its gravitational influence, dark energy seems almost completely disconnected from the material world. It doesn't clump together to form structures. It doesn't emit radiation or absorb light. It simply fills space uniformly, creating a smooth background pressure that pushes outward on the largest scales. This uniformity is both a clue and a puzzle. The fact that dark energy appears the same everywhere suggests it might indeed be a property of space itself rather than a substance that moves through space. But this very uniformity also makes it incredibly difficult to study. We can't point our telescopes at a particularly dense region of dark energy because no such regions seem to exist. Instead, we must infer its presence through its cumulative effects on the universe's expansion. It's like trying to understand the wind by watching how it moves the leaves on trees, except in this case, the leaves are entire galaxies, and the wind is an invisible force that fills all of space. The discovery of dark energy has also forced us to confront some uncomfortable truths about our place in the cosmos. Not only are we made of atoms that represent a tiny fraction of the universe's mass and energy, but we exist in a cosmos dominated by a force we don't understand. It's humbling to realize that our entire visible universe, all the stars and planets and galaxies we can see, represents less than 5% of what actually exists. This perspective shift is both unsettling and wonderful. Unsettling because it reminds us how much we still don't know about the reality we inhabit. Wonderful because it suggests that the universe still holds profound secrets waiting to be discovered, mysteries that could revolutionize our understanding of existence itself. As we drift deeper into this cosmic mystery, we'll explore the ingenious methods scientists use to study something invisible, the competing theories about what dark energy might actually be, and the profound implications this discovery holds for the ultimate fate of our universe. But for now, let yourself rest in the knowledge that you live in a cosmos far stranger and more magnificent than we ever dared imagine. A universe where the very fabric of space itself dances to rhythms we're only beginning to hear. The quest to understand dark energy has led astronomers to become cosmic detectives, hunting for clues in the most unlikely places. Since we can't observe dark energy directly, we must study its fingerprints, the subtle ways it leaves its mark on the universe around us. And remarkably, these fingerprints are everywhere once you know how to look for them. One of the most elegant methods involves studying the cosmic microwave background, that ancient afterglow of the Big Bang we touched on earlier. This faint radiation carries within it the imprint of tiny fluctuations that existed when the universe was just 380,000 years old, mere infancy in cosmic terms. These fluctuations, like ripples on the surface of a primordial pond, would eventually grow into the galaxies and galaxy clusters we see today. But here's the fascinating part. The pattern of these ancient ripples depends on the geometry of space itself. If dark energy is real and behaves as we think it does, it should leave a distinctive signature in this cosmic background radiation. It's like examining the grain in a piece of wood to understand the conditions in which the tree grew, except in this case, we're reading the grain of space itself to understand how the universe evolved. When scientists analyzed this ancient light with exquisite precision using satellites like the Wilkinson Microwave Anisotropy Probe and later the Planck mission, they found exactly the signatures that dark energy theory predicted. The universe appeared to be geometrically flat, meaning that parallel lines drawn across cosmic distances would remain parallel forever, never converging or diverging. This flatness, combined with the observed expansion rate, could only be explained if something like dark energy filled about 70% of the universe. Another powerful technique involves studying the large-scale structure of the cosmos itself, the way galaxies cluster together across vast distances. Think of it as cosmic archaeology, where the arrangement of galaxies today tells us about the forces that shaped them over billions of years. If dark energy has been influencing the expansion of space, it should have affected how these structures grew and evolved. Astronomers have mapped millions of galaxies across enormous volumes of space, creating three-dimensional maps of the cosmic web. These surveys, with names like the Sloan Digital Sky Survey and the Dark Energy Survey, reveal a universe that looks remarkably like a vast foam or sponge. Galaxies form sheets and filaments separated by enormous voids, creating a pattern that extends across hundreds of millions of light years. The statistics of this cosmic web, the way structures cluster at different scales, provides another independent confirmation of dark energy's existence. Without its influence, the universe would have evolved differently, creating a different pattern of galaxy distribution than what we actually observe. It's like being able to deduce the recipe for a cake by examining its final texture and structure. Perhaps most remarkably, astronomers have developed ways to measure dark energy's effects across cosmic time. By studying supernovae at different distances, they're essentially looking back through time, observing how dark energy's influence has changed as the universe aged. Remember, when we look at distant objects in space, we're seeing them as they were long ago, since their light has taken time to reach us. What this cosmic time machine reveals is a universe with a complex history. In the early cosmos, when matter and radiation were much denser, gravity dominated the expansion. The universe was still growing, but it was decelerating, slowing down as matter pulled back on itself through gravitational attraction. This makes intuitive sense, like a ball thrown upward that gradually slows due to Earth's gravitational pull. But as the universe continued to expand and matter became more dilute, dark energy's influence gradually became more important. Unlike matter, which becomes less dense as space grows, dark energy maintained its strength. Eventually, about 5 billion years ago, dark energy overtook gravity as the dominant force on cosmic scales. From that point forward, the expansion began to accelerate. This transition point, when the universe shifted from deceleration to acceleration, represents one of the most significant moments in cosmic history. It's when the character of our universe fundamentally changed, when the future switched from one of eventual gravitational collapse to one of eternal expansion. We happen to be born into a universe at just the right time to witness this cosmic adolescence, this transition from one phase of existence to another. The precision with which astronomers can now measure this cosmic history is truly remarkable. They can determine not just that dark energy exists, but how its strength has varied over billions of years. The current evidence suggests that dark energy's density has remained remarkably constant throughout cosmic time, consistent with Einstein's cosmological constant but still leaving room for more exotic possibilities. This consistency across time provides important clues about dark energy's nature. If it truly is the energy of empty space itself, we would expect it to remain constant as the universe evolves. But if it's some kind of dynamic field, we might expect to see variations in its strength over cosmic history. So far, the observations favor constancy, but the measurements are still improving, and future surveys may reveal subtle changes that could revolutionize our understanding. The tools astronomers use to study dark energy continue to evolve and improve. New telescopes like the Vera Rubin Observatory will survey unprecedented volumes of the sky, mapping billions of galaxies and discovering millions of supernovae. Space-based missions like the Nancy Grace Roman Space Telescope will study dark energy's effects with even greater precision, free from the blurring effects of Earth's atmosphere. These future observations may finally answer some of the fundamental questions about dark energy's nature. Is it truly constant, or does it change over time? Does it interact with other forms of matter and energy in ways we haven't yet detected? Could it be a sign that our understanding of gravity itself needs revision? But perhaps most intriguingly, these studies are beginning to reveal how dark energy might shape the ultimate fate of our universe. If dark energy remains constant and continues to accelerate the expansion, the cosmos faces a future very different from what earlier generations of scientists imagined. Rather than eventually collapsing back in on itself in a reverse of the Big Bang, the universe will continue expanding forever, growing ever larger and colder as the eons pass. In this scenario, the galaxies around us will eventually disappear beyond our cosmic horizon, racing away so fast that their light can no longer reach us. Stars will burn out one by one, leaving behind a cold, dark expanse, punctuated only by the occasional flash of particles annihilating in the quantum vacuum. It's a future that sounds melancholy, but it unfolds over timescales so vast that the entire history of our universe so far represents just the first chapter of an infinitely long story. Yet even this future isn't certain. If dark energy is not constant but instead changes over time, the universe's fate could be quite different. Some theoretical models suggest that dark energy might gradually weaken, allowing gravity to eventually win out and reverse the expansion. Others propose that dark energy could grow stronger, leading to a Big Rip scenario, where the acceleration becomes so extreme that it tears apart galaxies, stars, planets, and eventually even atoms themselves. These possibilities might sound like the stuff of science fiction, but they represent serious scientific scenarios based on our current understanding of physics. The fact that we can even contemplate such cosmic futures speaks to how far our knowledge has progressed, how we've gone from seeing the universe as a static, unchanging backdrop to recognizing it as a dynamic, evolving entity with its own dramatic story arc. What makes dark energy so captivating isn't just its mystery, but the way it connects the smallest scales of reality to the largest. The quantum fluctuations that might give rise to dark energy occur at distances smaller than atomic nuclei, yet their cumulative effect shapes the evolution of the entire observable universe. It's as if the universe has a kind of cosmic metabolism, where the tiniest quantum processes fuel the grandest transformations. This connection between the quantum and the cosmic represents one of the most profound puzzles in modern physics. We have successful theories that describe the very small, quantum mechanics, and successful theories that describe the very large, general relativity. But dark energy sits at the intersection of these realms, requiring us to understand how quantum effects might manifest on cosmic scales. Solving this puzzle may require new physics, new ways of thinking about space, time, and energy that go beyond our current theories. Some physicists believe that understanding dark energy will be the key to developing a theory of quantum gravity, the long-sought, unified description of all fundamental forces. Others suggest it might point toward the existence of extra dimensions, or reveal that our universe is just one of many in a vast multiverse. Whatever the answer turns out to be, the search for understanding dark energy is pushing the boundaries of human knowledge in the most fundamental ways. We're not just trying to understand what fills the space between galaxies. We're attempting to comprehend the very nature of space itself, the reason why anything exists at all rather than nothing. As you rest tonight, surrounded by the familiar comfort of your room, remember that the space around you, the emptiness between the atoms in your body, the vacuum between Earth and the distant stars, all of it might be filled with this mysterious dark energy. It's not empty space, but rather a dynamic, evolving medium that's quietly orchestrating the largest transformations in the cosmos. This invisible presence doesn't just exist in the distant reaches of intergalactic space. It's here, in this very room, woven into the fabric of reality at every scale. Yet it's so gentle, so subtle, that you can't feel its influence directly. Only by studying the largest structures in the universe can we detect its presence, like hearing a whisper that's too quiet to notice until you listen very carefully to the silence. And perhaps that's what makes dark energy so profoundly beautiful in its mystery. Here we are, conscious beings made of stardust and quantum fields, trying to understand a force that's simultaneously everywhere and nowhere, fundamental yet invisible. It's like trying to study the canvas while standing inside the painting, attempting to comprehend the very medium upon which our existence is drawn. The more we learn about dark energy, the more questions seem to multiply. Each answer we uncover reveals 3 new puzzles, like opening a cosmic nesting doll where each layer contains something more mysterious than the last. This isn't frustrating for scientists, though it's exactly what makes the universe so endlessly fascinating. We're not just collecting facts about space, we're uncovering the deep grammar of reality itself. Consider how strange it is that we can even detect something so elusive. We've never built an instrument that can measure dark energy directly. No detector has ever registered a single particle of it. No sensor has ever felt its touch. Yet through the accumulated weight of countless observations, through the careful study of light that's traveled for billions of years, we've managed to map its influence across the entire observable cosmos. It's rather like being a detective in a mystery where the culprit is invisible, leaves no fingerprints, and makes no sound. Yet everywhere you look, you find evidence of their presence. Doors that have been opened, objects that have been moved, patterns that speak of an intelligence at work. The universe has become our crime scene, and dark energy is the invisible presence we're trying to understand. The techniques astronomers use to study this cosmic mystery are marvels of human ingenuity. They measure the brightness of stellar explosions that occurred when the universe was half its current age. They analyze the subtle patterns in radiation that's been traveling through space since long before Earth existed. They map the positions of millions of galaxies, looking for statistical patterns that reveal how space itself has evolved. Each of these methods is like a different sense organ, a way of perceiving aspects of reality that our biological evolution never equipped us to detect. We've essentially given ourselves new forms of vision that can see across billions of light years, and new forms of hearing that can listen to the whispers of the cosmic microwave background. What these extended senses reveal is a universe far more dynamic than our ancestors ever imagined. Space isn't a passive stage where events unfold. It's an active participant in the cosmic drama. It stretches and flexes, responds to the matter and energy within it, and apparently contains its own intrinsic energy that drives its expansion ever faster. This realization has profound implications for how we think about existence itself. If space has properties, if it can contain energy and evolve over time, then perhaps nothingness isn't a meaningful concept at all. Perhaps there's no such thing as truly empty space, only different configurations of the quantum fields that fill reality at its deepest level. The quantum vacuum, that supposed emptiness between particles, turns out to be anything but empty. It's a bubbling foam of virtual particles popping in and out of existence, a sea of potential energy that might manifest as the dark energy we observe. The mathematics describing this quantum foam is beautiful and strange, suggesting that what we call empty space is actually the most energetic thing in the universe. But here's where the mystery deepens. If the quantum vacuum contains as much energy as the calculations suggest it should, the universe would be expanding so rapidly that atoms couldn't even hold together. Clearly, something is cancelling out most of this vacuum energy, leaving behind just the tiny amount we observe as dark energy. What that something is, and how it knows to leave behind exactly the right amount, remains one of physics' greatest puzzles. Some theorists propose that this cancellation might be exact, that some unknown symmetry in nature ensures that the vacuum energy is precisely zero. In this view, the dark energy we observe isn't vacuum energy at all, but something else entirely. Perhaps it's a slowly rolling field, like a ball balanced on a nearly flat hill, that will eventually change and alter the universe's fate. Others suggest that the cancellation is almost, but not quite perfect, leaving behind the small residue of energy we observe. This would require an extraordinary fine-tuning, a cosmic coincidence so precise that it seems to demand explanation. Why should the cancellation be so nearly perfect, yet not quite complete? These questions touch on some of the deepest issues in physics and philosophy. If the parameters of our universe had to be tuned with incredible precision to allow for the existence of stars, planets, and life, what does that tell us about the nature of reality? Are we incredibly fortunate to exist in such a finely balanced cosmos, or are there countless other universes with different properties, and we naturally find ourselves in one suitable for our existence? The anthropic principle, as this idea is known, suggests that the universe's properties might seem fine-tuned simply because we're here to observe them. Universes with different properties might exist, but they wouldn't contain observers capable of wondering about cosmic fine-tuning. It's a bit like a puddle of water marveling at how perfectly the hole it sits in matches its shape, not realizing that it has simply flowed to fit whatever depression it found. Yet, even if our universe is one of many, the existence of dark energy raises profound questions about the nature of physical law itself. Is the amount of dark energy truly a constant, or does it change over cosmic time in ways too subtle for us to detect? If it's changing, what determines the rate of change? And what might trigger more dramatic transformations in the future? Some of the most intriguing theoretical possibilities involve dark energy that varies over time. In these models, the field responsible for cosmic acceleration isn't static, but evolves as the universe ages. Perhaps it's slowly rolling down an energy landscape, like a ball moving down a very gentle slope. As it rolls, the expansion rate might change, potentially leading to dramatically different futures for our cosmos. These dynamic dark energy models open up fascinating scenarios for the universe's evolution. Perhaps the current period of accelerated expansion is just a phase, like cosmic adolescence, and the universe will eventually mature into a different state. Maybe dark energy will weaken over time, allowing gravity to slow and eventually reverse the expansion. Or perhaps it will grow stronger, leading to ever more rapid acceleration. Some models even predict that dark energy might undergo sudden transitions, like water freezing into ice. In these scenarios, the universe could experience dramatic phase changes that fundamentally alter the properties of space itself. Such transitions would be cosmological events of unimaginable magnitude, reshaping reality on the largest possible scales. The possibility of cosmic phase transitions raises questions about the stability of our current universe. We exist during an era when dark energy appears to be constant and well-behaved, driving a steady acceleration of cosmic expansion. But if dark energy can change, if it's capable of sudden transitions, then our seemingly stable cosmos might be more fragile than we realize. This isn't a cause for concern in any practical sense. Even the most dramatic cosmic phase transitions would occur over timescales that dwarf the entire history of human civilization. But the possibility reminds us that the universe we inhabit is not a fixed, eternal structure, but a dynamic, evolving system capable of profound transformations. The search for understanding dark energy has also led to remarkable technological innovations. The precision required to measure cosmic acceleration has pushed the development of new detectors, more sensitive telescopes, and more sophisticated analysis techniques. These tools, developed to study the largest scales in the universe, often find applications in entirely different fields, from medical imaging to quantum computing. There's something poetic about how our desire to understand the cosmos drives innovation that improves life on Earth. The same mathematical techniques used to map dark energy help optimize traffic flow in cities. The detector technologies developed for space telescopes find their way into medical scanners. The computer algorithms that process galaxy surveys advance artificial intelligence research. This cross-pollination between cosmic research and practical applications reflects a deep truth about scientific inquiry. When we push the boundaries of knowledge in any direction, the insights we gain often prove useful in unexpected ways. The universe seems interconnected, not just physically, but intellectually, with discoveries in one domain illuminating problems in others. As our understanding of dark energy continues to evolve, we're also developing new ways to think about the relationship between the observed and the unobservable. Dark energy reminds us that reality extends far beyond what we can directly perceive. Most of what exists remains hidden from our senses, detectable only through its subtle influences on the things we can observe. This humbling realization connects to broader questions about the nature of knowledge itself. How much of reality can we ultimately hope to understand? Are there fundamental limits to what conscious beings can discover about the universe they inhabit? Or will we continue pushing back the boundaries of the unknown, revealing ever deeper layers of cosmic mystery? The story of dark energy suggests that the universe still holds profound secrets, waiting to be uncovered by future generations of cosmic explorers. We've learned to detect its presence and measure its effects, but we're still far from understanding what it actually is or how it fits into the broader fabric of physical law. Perhaps that's exactly as it should be. A universe that revealed all its secrets easily would be a less interesting place to live. The fact that dark energy remains mysterious, that it challenges our most fundamental theories and forces us to reconsider our assumptions about space and time, makes our cosmos a place of endless wonder and discovery. As you drift towards sleep tonight, remember that you're floating through a universe filled with invisible energy, a cosmos where the space between your atoms pulses with quantum fluctuations, where the emptiness around you might be the most energetic thing in existence. You're part of a reality so strange and wonderful that we're still learning its most basic properties, still uncovering the forces that shape everything from the smallest scales to the largest. The dark energy that fills the universe isn't separate from you. It's part of the same cosmic story, the same unfolding drama of existence. Every breath you take, every thought you think, happens within this sea of mysterious energy. You are, quite literally, swimming through one of the deepest mysteries in all of science, carried along by forces we're only beginning to comprehend. And in that mystery lies both comfort and wonder. Comfort in knowing that the universe still holds secrets, that there are always new frontiers to explore and new questions to ask. Wonder in realizing that even our most advanced theories and most sensitive instruments have only begun to scratch the surface of what's truly out there, waiting to be discovered. The quest to understand dark energy has revealed just how much we still don't know about the fundamental nature of reality. It's a bit like discovering that the foundation of your house is made of something you can't identify, something that clearly holds everything together but defies every test you can devise to understand it. The more we learn, the more we realize how many assumptions we've made about the basic structure of existence. Consider the strange mathematics that describe dark energy's behavior. Unlike every other form of energy or matter we've encountered, dark energy appears to have what physicists call negative pressure. Now, pressure is something we're familiar with from everyday life. The air in a balloon pushes outward, creating positive pressure. But dark energy does something far more peculiar. It pulls on itself while simultaneously pushing space apart, creating a kind of tension that pervades every cubic centimeter of the universe. This negative pressure is what gives dark energy its repulsive gravitational effect. In Einstein's theory of relativity, it's not just mass and energy that create gravitational attraction, but also pressure. Positive pressure enhances gravitational pull, which is why the core of the Sun, under enormous pressure, generates such intense gravitational fields. But negative pressure does the opposite. It creates gravitational repulsion, pushing space apart rather than pulling it together. The mathematics are elegant in their simplicity, but the physical reality they describe is deeply counterintuitive. Imagine trying to compress a spring, only to find that the more you compress it, the harder it pushes back, not just against your hands, but against the very space around it. That's somewhat analogous to how dark energy behaves, except it's not a spring you can see or touch, it's the fabric of space itself. This negative pressure also explains why dark energy doesn't clump together like ordinary matter. Gravity normally causes things to attract each other and form structures, planets, stars, galaxies. But dark energy's gravitational effect is repulsive, so it naturally spreads itself uniformly throughout space. It's self-smoothing, like water finding its level, except instead of flowing downhill, it flows into a perfectly even distribution across all of space. The uniformity of dark energy creates both opportunities and challenges for scientists trying to study it. On one hand, because it's the same everywhere, any measurement we make of its effects should be representative of dark energy throughout the universe. We don't have to worry about finding a particularly dense region to study, because no such regions exist. On the other hand, this very uniformity makes dark energy incredibly difficult to probe in detail. We can't perform controlled experiments on it because we can't isolate it or concentrate it. We can't compare regions with more dark energy to regions with less, because such variations don't seem to exist. It's like trying to study the properties of air while living at the bottom of an ocean of it, unable to ever experience what it would be like without it. This has led scientists to develop increasingly sophisticated statistical techniques to extract information about dark energy from astronomical observations. They study the subtle correlations between galaxy positions across vast distances, looking for patterns that reveal how dark energy has influenced structure formation. They analyze the statistical properties of the cosmic microwave background, searching for signatures of dark energy in fluctuations that are smaller than 1 part in 100,000. These techniques require enormous datasets and powerful computers to process them. Modern dark energy surveys observe millions of galaxies and measure their properties with extraordinary precision. Each galaxy's position, brightness, and distance must be determined to high accuracy, and then sophisticated algorithms search for the subtle patterns that dark energy's influence would create. It's rather like being an archaeologist trying to understand an ancient civilization, except instead of digging through layers of sediment, you're sifting through layers of cosmic time. Each observation looks back to a different epoch in the universe's history, and by combining observations at many different distances, you can reconstruct how dark energy's influence has evolved over billions of years. The results of these painstaking analyses continue to point toward the same mysterious conclusion. Dark energy appears to behave exactly like Einstein's cosmological constant, a perfectly uniform energy density that remains constant throughout space and time. This consistency is both reassuring and puzzling. Reassuring because it suggests that our theoretical framework is on the right track, puzzling because it raises deep questions about why this particular value of energy density should exist. The amount of dark energy in our universe appears to be finely tuned in a way that's difficult to understand. If it were much larger, the universe would have expanded so rapidly that galaxies could never have formed. Stars wouldn't exist, planets wouldn't exist, and certainly life as we know it couldn't have emerged. If dark energy were much smaller, its effects would be negligible, and the universe's expansion would be dominated entirely by the gravitational attraction of matter. Instead, dark energy has just the right strength to become important at just the right time in cosmic history. For the first several billion years after the Big Bang, matter dominated the universe's evolution, allowing structures to form and grow. But as the universe expanded and matter became more dilute, dark energy's influence gradually became more important. The transition occurred at exactly the right moment to allow for a rich cosmic ecosystem of galaxies and stars while still driving the accelerated expansion we observe today. This apparent fine-tuning has led some scientists to propose that our universe might be just one of many in a vast multiverse, each with different amounts of dark energy. In this view, we naturally find ourselves in a universe with the right amount of dark energy for complexity and life to emerge, because universes with very different amounts wouldn't contain observers to ponder the question. The multiverse hypothesis is simultaneously compelling and troubling for scientists. Compelling because it could explain the apparent fine-tuning of cosmic parameters without requiring any special design or purpose. Troubling because it's extremely difficult to test experimentally. If other universes exist with different properties, they might be fundamentally unobservable from our own, making the multiverse hypothesis more philosophy than science. Yet, even within our single observable universe, dark energy continues to reveal new puzzles. Recent observations have hinted at possible variations in dark energy's effects across different regions of the sky. These variations are subtle and still debated, but if confirmed, they could indicate that dark energy isn't perfectly uniform after all, or that our understanding of its properties is incomplete. Some of these anomalies might point toward modifications of Einstein's theory of gravity on cosmic scales. Perhaps general relativity, so successful at describing everything from GPS satellite orbits to black hole mergers, needs adjustment when applied to the entire observable universe. Modified gravity theories attempt to explain cosmic acceleration without invoking dark energy at all, instead proposing that gravity itself behaves differently on the largest scales. These alternative theories face significant challenges in matching all the observational evidence, but they serve an important role in keeping scientists honest about their assumptions. Science progresses not just by confirming existing theories, but by challenging them, by asking whether there might be simpler or more elegant explanations for the phenomena we observe. The tension between different theoretical approaches to understanding cosmic acceleration reflects a deeper uncertainty about the nature of space and time themselves. Are space and time fundamental aspects of reality, or do they emerge from something more basic? Is the fabric of space-time truly smooth and continuous, or does it have a granular structure at the smallest scales? These questions connect dark energy research to some of the most profound problems in theoretical physics. The attempt to unify quantum mechanics with general relativity has led to various proposals for the fundamental nature of space and time. String theory suggests that space has extra dimensions beyond the three we experience directly. Loop quantum gravity proposes that space itself has an atomic structure made of discrete units of area and volume. If space truly has additional dimensions or a granular structure, these properties might manifest as effects we attribute to dark energy. Perhaps what we interpret as an intrinsic energy of empty space is actually the influence of hidden dimensions or quantum fluctuations in the fabric of space-time itself. The search for a deeper understanding of dark energy has also revealed unexpected connections between cosmology and particle physics. The energy scales involved in cosmic acceleration are incredibly tiny by particle physics standards, far smaller than the energies produced in our most powerful accelerators. Yet, understanding dark energy might require new insights into the fundamental forces and particles that govern reality at its deepest level. Some theoretical models propose that dark energy is associated with extremely light particles, so light that they've never been detected in laboratory experiments. These particles would fill the universe like a cosmic fluid, their collective behavior driving the accelerated expansion. Other models suggest that dark energy might be connected to the physics of phase transitions, like the way water transforms into steam when heated beyond a critical temperature. The possibility that dark energy involves new particles or new physics has motivated experimental searches beyond traditional astronomy. Underground laboratories search for hypothetical dark energy particles that might interact weakly with ordinary matter. Precision tests of gravity look for deviations from Einstein's predictions that might indicate the influence of extra dimensions or modified gravitational laws. These experiments represent a fascinating convergence of the very large and the very small. Scientists studying the expansion of the entire universe work alongside those probing the behavior of individual atoms and particles. The hope is that insights from both scales will eventually converge on a unified understanding of dark energy's true nature. Meanwhile, advances in observational technology continue to refine our measurements of dark energy's effects. New telescopes with unprecedented sensitivity are planned for both ground-based and space-based observations. These instruments will survey larger volumes of the universe with greater precision, potentially revealing subtle variations in dark energy's behavior that current observations can't detect. The next generation of dark energy surveys will observe billions of galaxies and measure their properties with extraordinary accuracy. They'll track how cosmic structures have grown and evolved over most of the universe's history, potentially revealing whether dark energy has remained truly constant or has changed in subtle ways over cosmic time. These future observations might finally answer some of the fundamental questions about dark energy's nature. If it's truly Einstein's cosmological constant, it should remain perfectly constant throughout space and time. But if it's a dynamical field of some kind, future surveys might detect the subtle variations that would reveal its true identity. The implications of these discoveries could be profound. If dark energy is found to vary over time, it could indicate that our universe is approaching another phase transition, a cosmic transformation that could fundamentally alter the nature of space itself. If it's found to vary across space, it might reveal new insights into the structure of reality at the largest scales. But perhaps most remarkably, the study of dark energy has shown us that the universe still holds secrets far beyond what we ever imagined. Here we are, conscious beings who have learned to split atoms and sequence genomes and send robots to other planets, yet we've discovered that we don't understand what makes up most of our own universe. It's a humbling reminder that for all our technological prowess, we're still taking our first tentative steps toward understanding the true nature of existence. This ignorance isn't a cause for despair, but rather a source of wonder and motivation. Every mystery solved reveals new questions. Every answer opens new avenues of exploration. Dark energy reminds us that the universe is far stranger and more beautiful than we can currently comprehend, filled with phenomena that challenge our most basic assumptions about reality. As you settle into sleep tonight, consider that you're drifting through a cosmos where empty space itself might be the most mysterious thing in existence. The vacuum around you, the gaps between atoms in your body, the vast reaches between stars, all of it potentially filled with an energy we can detect but cannot yet understand. You're floating in an ocean of mystery that extends from the quantum realm to the cosmic horizon. This mysterious energy doesn't just exist in the distant reaches of intergalactic space. It's here, in this very moment, woven into the fabric of the space you occupy. Yet it's so subtle, so gentle in its influence, that you can't feel it directly. Only by studying the motion of galaxies billions of light years away can we detect its presence, like hearing an impossibly quiet song that only becomes audible when you listen to the entire cosmic chorus. The mathematics describing dark energy are beautiful in their simplicity, elegant equations that capture something profound about the nature of space and time. Yet these equations describe a reality so strange that we struggle to find adequate metaphors or analogies. How do you explain something that has the gravitational effect of pushing rather than pulling? How do you describe an energy that grows stronger as space expands rather than weaker? Perhaps the closest analogy is to think of space itself as having a kind of springiness, an intrinsic tendency to expand that becomes more apparent as cosmic structures spread apart. This springiness isn't something added to space from outside. It's a fundamental property of the vacuum itself, like the way certain materials naturally expand when heated, except in this case, the expansion is driven by the vacuum's own internal energy. This perspective suggests that what we call empty space isn't really empty at all, but rather the most active, energetic thing in the universe. The quantum fields that fill the vacuum are constantly fluctuating, creating virtual particles that pop in and out of existence in timescales so brief that we can barely measure them. These fluctuations might be the source of dark energy, the reason why space has its mysterious tendency to expand. Yet, if quantum fluctuations are responsible for dark energy, they must be incredibly well controlled. The calculations suggest that these fluctuations should produce far more vacuum energy than we observe, enough to prevent atoms from forming or stars from shining. Something must be regulating these fluctuations, fine-tuning them to produce exactly the amount of dark energy we see. This fine-tuning problem is one of the most profound puzzles in all of physics. It suggests that there might be fundamental principles or symmetries in nature that we don't yet understand, hidden mechanisms that ensure the vacuum energy takes exactly the value needed for a universe like ours to exist. Some theorists propose that this fine-tuning might be the result of a cosmic selection process, where universes with the wrong amount of vacuum energy simply don't survive long enough to develop complexity. Others suggest that the fine-tuning might be exact rather than approximate, that some unknown principle sets the vacuum energy to precisely zero, and what we observe as dark energy has a completely different origin. These possibilities point toward physics beyond our current theories, new principles that could revolutionize our understanding of space, time, and energy. The search for these principles drives some of the most ambitious research in theoretical physics, from attempts to unify all the fundamental forces to explorations of how consciousness might emerge from quantum processes. The mystery of dark energy also raises profound questions about the relationship between mind and cosmos. How is it that conscious beings made of ordinary matter can study and understand, however incompletely, the invisible energy that dominates their universe? What does it mean that the cosmos has evolved to the point where parts of it can contemplate their own existence and try to understand the forces that shape them? These questions don't have clear scientific answers, but they point towards something remarkable about the universe we inhabit. Despite being made of what appears to be a tiny fraction of cosmic material, despite existing for what seems like an instant in cosmic time, we've somehow developed the ability to probe the deepest mysteries of existence. We can detect the influence of forces we can't see, measure the properties of fields we can't touch, and contemplate the ultimate fate of everything that exists. This capacity for cosmic understanding might be the most mysterious thing of all. Here we are, temporary arrangements of atoms and energy, somehow capable of grasping mathematical relationships that govern the behavior of space itself. We can write equations that describe how the universe expands, build instruments that detect light from the cosmic dawn, and formulate theories about the fundamental nature of reality. Perhaps consciousness itself is as mysterious and fundamental as dark energy, another aspect of the universe that we can observe and study but don't yet truly understand. Both consciousness and dark energy seem to emerge from the basic properties of space and matter, yet both remain profound mysteries despite our best efforts to explain them. As you drift towards sleep, remember that you're part of this cosmic mystery, a conscious observer floating through a universe filled with invisible energy. The thoughts you're having right now, the dreams that will soon come, all of it happens within this sea of dark energy that we're only beginning to understand. You are simultaneously infinitely small in cosmic terms and infinitely precious as one of the few arrangements of matter that can contemplate its own existence. The universe has spent billions of years arranging itself in just the right way to produce moments like this one, where consciousness meets cosmos in quiet wonder. Dark energy has been patiently shaping space, driving expansion, preparing the cosmic stage for the emergence of complexity and awareness. In a very real sense, the mysterious force that fills empty space has helped create the conditions necessary for your existence, for your ability to think and dream and wonder about the nature of reality itself. And tomorrow, when you wake, that same dark energy will still be there, still gently stretching space, still driving the grand expansion that began with the Big Bang and continues with each passing second. The mystery will remain, patient and profound, waiting for future generations of cosmic explorers to unlock its secrets and reveal the next chapter in our understanding of the universe we call home. The story of dark energy becomes even more intriguing when we consider how it might connect to other cosmic mysteries. You see, dark energy isn't the only invisible component of our universe. There's also dark matter, that strange substance that holds galaxies together through its gravitational pull, but refuses to interact with light in any way we can detect. Together, dark energy and dark matter make up about 95% of everything that exists, leaving ordinary matter, the stuff that makes up stars and planets and you and me, as a mere 5% of cosmic reality. This creates a rather humbling picture of our place in the universe. We're not just living on a small planet orbiting an ordinary star in an unremarkable galaxy. We're made of the rarest kind of material in the cosmos, a tiny fraction of reality that happens to be the only kind we can directly perceive and interact with. It's a bit like discovering that you've been living your entire life in a house where 95% of the rooms are invisible, and you can only experience the small, visible portion. The relationship between dark energy and dark matter adds layers of complexity to our cosmic story. While dark matter clumps together through gravity, forming the invisible scaffolding upon which galaxies are built, dark energy remains uniformly spread throughout space, pushing against the very expansion that dark matter's gravity tries to slow. It's as if the universe contains two competing invisible influences, one trying to pull things together, the other trying to push everything apart. This cosmic tug-of-war has played out over billions of years, shaping the evolution of everything we see in the night sky. In the early universe, when matter was much denser, dark matter's gravitational influence dominated. It helped pull together the first stars and galaxies, creating the cosmic web of structure that telescopes reveal today. But as the universe expanded and matter became more dilute, dark energy's influence grew stronger, eventually winning the competition and driving the accelerated expansion we observe. The timing of this transition is remarkably significant. If dark energy had dominated too early in cosmic history, galaxies would never have formed. The expansion would have been so rapid that matter couldn't clump together under its own gravity. Stars wouldn't have ignited, heavy elements wouldn't have been forged, and planets like Earth couldn't have formed. The universe would have remained a cold, empty expanse of hydrogen and helium, forever expanding but never developing the complexity that makes life possible. On the other hand, if dark energy had remained weak for too long, gravity would have eventually reversed the cosmic expansion entirely. The universe would have collapsed back in on itself, in a reverse of the Big Bang, crushing everything that had ever formed into a final cosmic crunch. Again, No stars, no planets, no life, no consciousness to ponder the mysteries of existence. Instead, we find ourselves in a universe where these two invisible influences are balanced just right, at least for now. Dark matter provided the gravitational seeds that grew into galaxies and stars, while dark energy waited patiently in the background, its influence growing as space expanded. The transition between their dominance occurred at exactly the right moment to allow for a rich, complex cosmos filled with structure and light. This exquisite timing raises profound questions about the nature of cosmic coincidences. Is our universe simply extraordinarily fortunate, or is there some deeper principle that ensures the right balance between these competing influences? Some scientists propose that the apparent fine-tuning might be the result of a selection effect. If countless universes exist with different properties, we naturally find ourselves in one where the conditions are right for observers to exist, simply because universes without such conditions wouldn't contain anyone to notice them. But even if our universe is one of many, the specific properties of dark energy remain deeply puzzling. The amount of dark energy we observe seems to require incredibly precise fine-tuning, not just in its overall strength, but in how that strength relates to other fundamental constants of nature. Change any of these parameters by even a tiny amount, and you get a universe that looks nothing like the one we inhabit. This precision suggests that dark energy might be connected to other aspects of physics in ways we don't yet understand. Perhaps it's related to the fundamental forces that govern particle interactions, or to the geometry of the extra dimensions that string theory proposes, or to some cosmic mechanism that automatically adjusts the vacuum energy to just the right value. The search for these deeper connections has led physicists to explore increasingly exotic possibilities. Some theories propose that dark energy might be cyclical, growing stronger and weaker over cosmic time in regular patterns. In these models, our universe might undergo periodic phases of acceleration and deceleration, expanding rapidly for billions of years before entering a phase where gravity regains dominance and structures can form and evolve. Other theories suggest that dark energy might interact with dark matter in subtle ways we haven't yet detected. Perhaps these two mysterious components of our universe aren't completely separate phenomena, but rather different aspects of a single underlying field that manifests differently under different conditions. Such interactions could leave signatures in the cosmic microwave background or in the distribution of galaxies that future observations might detect. The possibility of dark energy interactions opens up fascinating scenarios for cosmic evolution. If dark energy can change over time or interact with other forms of matter and energy, then the universe's future might be far more dynamic than current models suggest. Rather than expanding forever at an ever-increasing rate, the cosmos might undergo transitions to entirely new phases of existence. Imagine a universe where dark energy gradually transforms into something else, perhaps a field that drives contraction rather than expansion. Such a transformation wouldn't happen overnight, of course. It would unfold over timescales that make the entire history of our universe seem brief. But eventually, the cosmic expansion would slow, stop, and reverse, leading to a phase where galaxies rush toward each other rather than apart. Or consider the possibility that dark energy might undergo sudden transitions, like water freezing into ice. In such scenarios, the universe could experience abrupt changes in its expansion rate, perhaps entering phases where space itself develops new properties. The laws of physics as we know them might remain valid, but the cosmic environment in which they operate could be transformed beyond recognition. These speculative possibilities remind us that our current understanding of dark energy represents just the beginning of a much larger story. We've detected its presence and measured some of its properties, but we're still far from comprehending what it actually is, or how it fits into the broader tapestry of physical law. The universe continues to hold secrets that challenge our most fundamental assumptions about the nature of reality. The instruments and techniques used to study dark energy continue to evolve rapidly. New telescopes with unprecedented sensitivity are being built to survey ever larger volumes of space with greater precision. These next-generation observatories will map billions of galaxies, track the motions of countless stellar explosions, and measure the subtle distortions that dark energy creates in the fabric of space itself. Space-based telescopes offer particular advantages for dark energy research because they can observe without the blurring effects of Earth's atmosphere. Future space missions will track how cosmic structures have evolved over most of the universe's history, potentially revealing whether dark energy has remained constant or has changed in ways too subtle for current instruments to detect. The data from these future surveys will be staggering in its volume and complexity. Analyzing the positions and properties of billions of galaxies requires sophisticated algorithms and enormous computing power. Scientists are developing new statistical techniques and machine learning approaches to extract the subtle signals of dark energy from the cosmic data deluge. These technological advances aren't just tools for studying dark energy. They're pushing the boundaries of human capability in fundamental ways. The precision required to measure cosmic acceleration has driven innovations in detector design, data analysis, and theoretical modeling that find applications far beyond astronomy. The quest to understand the universe's most mysterious component is advancing our technological capabilities across many fields. But perhaps most remarkably, the study of dark energy is revealing just how interconnected the cosmos truly is. The same force that drives cosmic expansion on the largest scales might be intimately connected to the quantum processes occurring at the smallest scales. The energy that fills empty space might be related to the fundamental particles and forces that govern all matter and energy. This interconnectedness suggests that understanding dark energy will require not just better telescopes and more sensitive detectors, but new ways of thinking about the relationship between different scales of reality. We might need to develop theories that seamlessly connect the quantum world of particles and fields to the cosmic world of galaxies and expansion, bridging the gap between the infinitely small and the infinitely large. The challenge is both technical and conceptual. We need new mathematics to describe phenomena that exist at the intersection of quantum mechanics and general relativity. We need new experimental techniques to test theories about forces and fields that operate on cosmic scales. And we need new philosophical frameworks to understand what it means for conscious beings to exist in a universe dominated by invisible energy. This last point is particularly intriguing. The fact that we can study dark energy at all seems almost miraculous when you consider the vast scales and subtle effects involved. We're using instruments barely larger than ourselves to detect influences that operate across billions of light years. We're employing mathematical techniques developed by human minds to understand forces that were shaping the cosmos long before Earth existed. There's something profoundly moving about this cosmic detective work. Here we are, temporary arrangements of atoms and energy, somehow capable of comprehending the forces that govern the largest structures in existence. We can write equations that describe the behavior of invisible fields, build instruments that detect their subtle influences, and formulate theories about their ultimate nature. This capacity for cosmic understanding might be related to the very properties of space and time that dark energy helps to shape. Perhaps the uniform expansion driven by dark energy creates the stable cosmic environment necessary for complex structures like stars and planets to form. Perhaps the gentle acceleration provides just the right balance between order and chaos for consciousness to emerge and flourish. In this view, dark energy isn't just a mysterious force that happens to fill our universe. It's an essential ingredient in the cosmic recipe that makes awareness possible. Without it, the universe might have collapsed too quickly for life to develop, or expanded too slowly for the diversity of environments that biological evolution requires. The invisible energy that drives cosmic expansion might be directly responsible for creating the conditions that allow minds like ours to contemplate their own existence. This perspective suggests a deep connection between the physical properties of the universe and the emergence of consciousness. We're not separate observers studying an alien cosmos from the outside. We're integral parts of the cosmic story, products of the same physical processes that created stars and galaxies, and the mysterious energy that fills empty space. The dark energy that surrounds you right now isn't separate from your existence. It's part of the same cosmic web that includes your thoughts, your dreams, and your capacity for wonder. The space between the atoms in your body pulses with the same quantum fluctuations that might give rise to cosmic acceleration. The vacuum around you participates in the same mysterious dance of energy and geometry that shapes the evolution of the entire universe. As you rest tonight, remember that you're floating through a cosmos where the deepest mysteries are also the most fundamental realities. Dark energy isn't just an abstract concept from physics textbooks. It's the invisible medium through which you move, the subtle presence that helps determine the ultimate fate of everything that exists. It's been shaping space since long before you were born, and it will continue its patient work long after your atoms have returned to the cosmic cycle. Yet in this moment, in this brief intersection of consciousness and cosmos, you have the remarkable privilege of contemplating these mysteries. You can think about forces that operate on scales vastly larger than anything in your direct experience. You can ponder the nature of space and time and energy in ways that would have been impossible for any conscious being throughout most of cosmic history. This capacity for wonder and understanding might be the most mysterious thing of all. How did the universe arrange itself in such a way that parts of it can contemplate the whole? How did matter and energy, shaped by forces like dark energy over billions of years, eventually give rise to minds capable of studying those very forces? These questions don't have clear answers, but they point towards something profound about the relationship between mind and cosmos. Perhaps consciousness and dark energy are both aspects of the same underlying reality, different manifestations of the universe's capacity for complexity and self-organization. Perhaps the same principles that drive cosmic expansion also drive the emergence of awareness, the development of curiosity, and the growth of knowledge and understanding. In this view, your thoughts about dark energy aren't separate from dark energy itself. They're part of the same cosmic story, expressions of the universe's ongoing evolution toward greater complexity and deeper self-awareness. When you wonder about the nature of space and time, you're participating in the cosmos's attempt to understand itself, to know its own deepest properties and principles. The mystery of dark energy reminds us that this cosmic journey of discovery has only just begun. We've learned to detect its presence and measure some of its effects, but we're still taking our first tentative steps toward true understanding. The universe continues to hold secrets that will challenge and inspire future generations of explorers, mysteries that will require new forms of mathematics, new experimental techniques, and perhaps new ways of thinking about reality itself. But that's part of what makes existence so remarkably beautiful. We live in a cosmos that rewards curiosity, that reveals new wonders to those patient enough to look carefully and think deeply. Dark energy represents one of the greatest puzzles we've ever encountered, but it's also an invitation to push the boundaries of human knowledge and capability. As you drift towards sleep, carried along by the gentle expansion of space itself, remember that you're part of this ongoing adventure of discovery. The questions we're asking about dark energy today might be answered by minds that don't yet exist, using technologies we haven't yet imagined. But those future discoveries will build on the work being done right now, the careful observations and theoretical insights that are slowly revealing the nature of the invisible energy that fills our universe. The cosmos is patient with our ignorance, generous with its mysteries, and endlessly surprising in its revelations. Dark energy is just one chapter in a story that connects the quantum realm to the cosmic horizon, that links the emergence of consciousness to the evolution of space itself. It's a story in which you play an essential part, not as a passive observer, but as an active participant in the universe's journey towards self-understanding. And in that participation lies both wonder and responsibility. The capacity to contemplate cosmic mysteries is a gift that comes with the obligation to use it wisely, to continue the ancient human tradition of asking deep questions about the nature of existence. Whether dark energy turns out to be the energy of empty space, a new kind of field, or something even more exotic, the search for understanding will continue to reveal new aspects of the cosmic story we all share. Tomorrow, when you wake, that same mysterious energy will still be there, still gently stretching space, still shaping the evolution of everything that exists. The mystery will remain, patient and profound, waiting for the next breakthrough in understanding, the next insight that will illuminate another aspect of the invisible force that governs the fate of the cosmos. And you'll still be part of that story, carried along by the expansion of space itself, swimming through an ocean of dark energy toward whatever revelations await in the vast, mysterious future of our universe. Tonight, as we continue our gentle drift through the cosmic mysteries surrounding dark energy, let's explore what this invisible force might mean for the very fabric of reality itself. Because you see, dark energy doesn't just affect the distant reaches of intergalactic space. It's woven into the fundamental structure of existence at every scale, from the quantum realm beneath your fingertips to the vast cosmic web that stretches across billions of light years. Consider for a moment the space around you right now. Between your body and the walls of your room, between the molecules in the air you breathe, even between the atoms that make up your own cells, there exists what we call the quantum vacuum. Now, vacuum might sound like emptiness, like nothing at all, but quantum mechanics tells us something far more intriguing. This apparent nothingness is actually a bubbling sea of activity, filled with virtual particles that pop into existence for the briefest of instants, before vanishing back into the void. These quantum fluctuations are so fleeting, so ephemeral, that they exist for timescales shorter than anything we can directly measure. Yet their cumulative effect might be responsible for the dark energy that drives our universe's expansion. It's as if the very act of existing, of space, simply being space, creates a subtle pressure that pushes outward against gravity's inward pull. But here's where the mystery deepens into something almost paradoxical. When physicists calculate how much energy these quantum fluctuations should produce, they arrive at a number so astronomically large that it would tear apart every atom in the universe within the first fraction of a second after the Big Bang. The fact that we're here, that galaxies exist, that you can breathe and think and wonder about these questions, means that something must be cancelling out almost all of this quantum energy, leaving behind only the tiniest residue that we observe as dark energy. This cancellation would need to be precise beyond anything we've ever encountered in physics. Imagine trying to balance two enormous weights on a scale, each weighing as much as all the galaxies in the observable universe, and getting them to balance so perfectly that only a feather's worth of difference remains. That's the level of precision required to explain why our universe hasn't been torn apart by its own quantum energy. Some theorists propose that this near-perfect cancellation might not be a coincidence, but rather a sign of some deeper symmetry in nature, some fundamental principle that automatically keeps the vacuum energy in check. Others suggest that the cancellation might be exact, that some unknown mechanism sets the quantum contribution to precisely zero, and that dark energy has an entirely different origin. These possibilities point toward physics beyond our current understanding, new principles that could revolutionize how we think about the relationship between space, time, and energy. Perhaps the vacuum isn't just the stage upon which particles and fields perform their dance, but an active participant with its own complex dynamics and hidden properties. The implications ripple outward in fascinating directions. If space itself has energy, if the vacuum can influence the expansion of the universe, then perhaps our traditional distinction between something and nothing needs revision. Maybe there's no such thing as true emptiness, only different configurations of the fields that fill reality at its deepest level. This perspective transforms how we might think about existence itself. The space in your room, the gap between your thoughts, the pause between heartbeats, all of it potentially filled with this mysterious energy that connects the quantum world to the cosmic scale. You're not sitting in empty space, but rather floating in a sea of invisible activity, surrounded by the same forces that shape galaxies and drive the expansion of everything that exists. The search for a deeper understanding of dark energy has led scientists to explore connections between seemingly unrelated areas of physics. Some theories suggest that dark energy might be related to the fundamental forces that govern particle interactions. Perhaps the same mechanisms that give particles their masses also contribute to the energy density of empty space. Or maybe dark energy is connected to the way information is processed and stored in quantum systems, linking the expansion of the universe to the fundamental nature of knowledge itself. These speculative connections hint at a universe far more integrated than we might have imagined. Rather than consisting of separate components, matter, energy, space, and time, reality might be a single, unified system where each aspect influences all the others. Dark energy wouldn't just be another ingredient in the cosmic recipe, but rather an expression of how all the other ingredients interact and evolve together. The mathematical descriptions of dark energy reveal patterns that appear throughout physics in unexpected contexts. The equations that describe how dark energy affects cosmic expansion are related to those that govern phase transitions in materials, the formation of patterns in complex systems, and even the dynamics of information flow in networks. It's as if the universe uses the same mathematical language to describe phenomena across vastly different scales and contexts. This mathematical unity suggests that dark energy might be part of a broader tapestry of physical law, connected to principles we're only beginning to discover. Perhaps understanding its true nature will require new mathematical frameworks that can describe how quantum effects manifest on cosmic scales, or how information and consciousness emerge from the fundamental properties of space and time. The technological challenges of studying dark energy have pushed the development of instruments and techniques that barely seemed possible just a few decades ago. Modern surveys map the positions and properties of millions of galaxies with precision that would have been unimaginable to earlier generations of astronomers. These massive datasets require sophisticated algorithms and powerful computers to analyze, driving advances in data science and machine learning that find applications far beyond cosmology. But perhaps most remarkably, the study of dark energy has revealed just how much the universe still has to teach us. Despite centuries of scientific progress, despite our ability to predict eclipses and build computers and sequence genomes, we've discovered that we don't understand what makes up most of our own cosmos. It's a humbling reminder that the journey of discovery has only just begun, that reality holds secrets we haven't even learned how to ask about yet. This vast ignorance isn't a failure of science, but rather a testament to the universe's inexhaustible richness. Every answer we uncover reveals new questions. Every solved mystery points toward deeper puzzles. Dark energy represents one of the most profound challenges we've ever encountered, but it's also an invitation to expand our understanding in directions we never anticipated. The implications extend beyond physics into philosophy and our understanding of what it means to exist in such a universe. If most of reality consists of invisible energy and matter that we can barely detect, what does that tell us about the nature of knowledge itself? Are there fundamental limits to what conscious beings can understand about their cosmos? Or will we continue pushing back the boundaries of the unknown indefinitely? These questions become even more intriguing when we consider that consciousness itself might be as mysterious as dark energy. Here we are, temporary arrangements of atoms and electrical signals, somehow capable of contemplating forces that operate across billions of light years and billions of years of cosmic time. The fact that matter can organize itself into patterns capable of self-awareness and cosmic understanding might be as remarkable as any force that shapes the expansion of space. Perhaps there's a deep connection between the emergence of consciousness and the properties of the universe that make complex structures possible. Dark energy helps create a cosmos where galaxies can form and persist, long enough for stars to shine and planets to develop rich chemistry. Without its influence, the universe might have collapsed too quickly or expanded too rapidly for the intricate dance of matter and energy that eventually leads to life and awareness. In this view, the mysterious force that fills empty space isn't separate from your capacity to think and wonder about it. They're both expressions of the same underlying reality, different aspects of a universe that seems almost designed to foster complexity, consciousness, and the growth of knowledge. The dark energy that drives cosmic expansion might be intimately connected to the processes that allow minds to emerge and contemplate their own existence. This connection between the cosmic and the conscious becomes even more intriguing when we consider the role of observation in quantum mechanics. Some interpretations suggest that consciousness plays a fundamental role in determining the properties of quantum systems, that the act of observation somehow helps collapse the wave function and determine which of many possible outcomes actually occurs. If this is true, then conscious beings aren't just passive observers of the universe, but active participants in its ongoing evolution. The implications are both beautiful and mysterious. Perhaps the universe needs conscious observers, not just to understand its properties, but to help determine them. Maybe the dark energy that shapes cosmic expansion is influenced, in ways we can't yet fathom, by the very minds that have evolved to study it. The boundary between observer and observed might be far more fluid than we typically assume. These speculative possibilities remind us that science is not just about collecting facts, but about developing new ways of thinking about reality itself. The discovery of dark energy has forced us to question our most basic assumptions about space, time, and energy. It's shown us that the universe is stranger and more mysterious than we ever imagined, filled with phenomena that challenge our understanding at the deepest level. But this strangeness is also what makes existence so wonderfully rich with possibility. We live in a cosmos that rewards curiosity, that reveals new layers of complexity and beauty to those patient enough to look carefully and think deeply. Dark energy represents just one thread in a vast tapestry of mysteries that connect the smallest scales to the largest, the most ancient past to the furthest future. The questions we're asking about dark energy today will likely seem quaint to future generations who have developed new ways of thinking about space and time. But those future insights will build on the work being done now, the careful observations and theoretical developments that are slowly revealing the nature of the invisible energy that permeates our universe. As you rest tonight, surrounded by this mysterious energy, remember that you're part of an ongoing story of discovery that stretches back through generations of curious minds and forward into a future filled with possibilities we can't yet imagine. The dark energy that fills the space around you connects you to the largest structures in the cosmos and to the deepest questions about the nature of existence itself. The vacuum between your atoms participates in the same quantum dance that might drive cosmic expansion. The space in your room shares the same mysterious properties as the vast reaches between galaxies. You're not separate from the cosmic mystery, but embedded within it, made of the same fundamental ingredients that compose stars and space and the invisible energy that shapes the fate of everything that exists. This intimate connection between your existence and the deepest mysteries of the cosmos is perhaps the most remarkable thing of all. In a universe dominated by invisible forces, you represent something extraordinary, a temporary arrangement of matter and energy that has somehow achieved the capacity for wonder, for curiosity, for the desire to understand the very forces that created the conditions for your existence. The search for understanding dark energy is really a search for understanding ourselves, our place in the cosmic order, and the remarkable fact that the universe has evolved to the point where parts of it can contemplate the whole. Whether dark energy turns out to be the quantum energy of empty space, a new kind of field, or something even more exotic, the journey of discovery will continue to reveal new aspects of the magnificent, mysterious reality we call home. And in that ongoing journey lies both comfort and excitement. Comfort in knowing that the universe still holds profound secrets, that there are always new frontiers to explore and new questions to ask. Excitement in realizing that we're living at a remarkable moment in cosmic history, when conscious beings are first beginning to probe the deepest mysteries of existence, and to understand the invisible forces that have been shaping reality since the very beginning of time. Tomorrow, the dark energy will still be there, still gently stretching space, still influencing the evolution of galaxies and the ultimate fate of the cosmos. The mystery will remain patient and profound, waiting for the next breakthrough in understanding that will illuminate another piece of the cosmic puzzle. And you'll still be part of that story, carried along by the expansion of space itself, floating through an ocean of invisible energy toward whatever revelations await in the vast, unknowable future of our endlessly surprising universe. The quest to understand dark energy has also opened up entirely new ways of thinking about the relationship between time and causality itself. You see, if dark energy truly represents the intrinsic energy of empty space, then it suggests something rather profound about the nature of time's passage. Unlike other forms of energy that dilute and weaken as the universe expands, dark energy maintains its density, as if time itself is constantly creating new energy to fill the growing volume of space. This peculiar behavior challenges our intuitive understanding of conservation laws. In most situations, energy can neither be created nor destroyed, only transformed from one form to another. But dark energy seems to violate this principle in the most elegant way possible. As space grows larger, more dark energy appears, not drawn from some external reservoir, but seemingly conjured from the very act of expansion itself. Some physicists have proposed that this apparent creation of energy might not violate conservation laws at all, but rather reveal something deeper about how those laws operate on cosmic scales. Perhaps what we call the conservation of energy is only a local approximation, valid in small regions of space and short periods of time, but requiring modification when applied to the universe as a whole. The expanding cosmos might possess a kind of cosmic metabolism, where the growth of space itself generates the energy needed to fuel further expansion. This perspective transforms our understanding of cosmic evolution from a simple story of expansion and cooling into something far more dynamic and self-sustaining. Rather than a universe that's gradually running down, using up its initial energy endowment from the Big Bang, we might inhabit a cosmos that's continuously regenerating itself, creating new energy as it grows and evolves. The implications ripple through every aspect of cosmology. If the universe can create energy through expansion, then perhaps it can create other things as well. Some theories suggest that the quantum fluctuations in empty space might occasionally produce not just virtual particles but real ones, actual matter that enriches the cosmic inventory as time progresses. The vacuum wouldn't just be the stage for physical processes, but an active participant, continuously adding new actors to the cosmic drama. These ideas connect to some of the most speculative frontiers in theoretical physics. String theory, that ambitious attempt to unify all fundamental forces, predicts the existence of extra dimensions beyond the three spatial dimensions we experience directly. If these extra dimensions are real, they might serve as reservoirs of energy that leak into our familiar three-dimensional space, manifesting as the dark energy we observe. Imagine space as a vast membrane floating in a higher dimensional realm, like a soap bubble suspended in air. The energy from these higher dimensions might seep through the membrane, creating a subtle pressure that drives cosmic expansion. In this view, our entire universe would be just one layer in a much larger multidimensional reality, influenced by forces and energies from realms we can barely imagine. Other theories propose even more exotic possibilities. Perhaps our universe is embedded in a network of interconnected cosmic structures, with dark energy representing the influence of neighboring universes pressing against our own. Or maybe the expansion we observe is driven by the universe's attempt to maintain some kind of cosmic equilibrium, balancing forces that operate according to principles we haven't yet discovered. The mathematical frameworks needed to describe these possibilities push the boundaries of human knowledge in remarkable ways. Physicists work with equations that describe spaces with 11 dimensions, particles that exist in multiple states simultaneously, and fields that can tunnel between different vacuum configurations. The mathematics is beautiful and strange, revealing patterns and symmetries that seem to point toward deeper truths about the nature of reality. But perhaps most remarkably, these abstract mathematical structures make concrete predictions about things we can actually observe. The extra dimensions of string theory should leave subtle signatures in the cosmic microwave background. The influence of neighboring universes should create patterns in the distribution of galaxies. The quantum tunneling of fields should produce specific kinds of fluctuations in dark energy strength over cosmic time. This connection between abstract theory and observable reality represents one of the most remarkable aspects of modern physics. We can write equations describing phenomena that exist far beyond our direct experience. Yet these equations make predictions about measurements we can perform with telescopes and detectors. It's as if mathematics provides a kind of cosmic language, allowing us to communicate with the universe about its deepest properties. The precision required for these tests continues to drive technological innovation in extraordinary directions. Future dark energy surveys will need to measure the positions of galaxies to accuracies better than the width of a human hair viewed from across a football field. They'll track changes in cosmic expansion that amount to less than a few centimeters per second across distances of billions of light years. Achieving such precision requires not just better instruments, but better understanding of all the subtle effects that could contaminate the measurements. Astronomers must account for how light bends around massive galaxy clusters, how dust in our own galaxy affects observations of distant objects, and how the Earth's motion through space influences what we see. Each of these effects must be modelled and corrected with extraordinary care. The data analysis techniques being developed for dark energy research represent marvels of statistical sophistication. Scientists use algorithms that can find subtle correlations in datasets containing billions of measurements, techniques that can separate genuine cosmic signals from instrumental noise and systematic errors. These methods often borrow ideas from machine learning and artificial intelligence, creating hybrid approaches that combine human insight with computational power. Yet, for all this technological sophistication, the fundamental mystery of dark energy remains as profound as ever. We can measure its effects with increasing precision, we can constrain its properties with ever greater accuracy, but we still don't know what it actually is. It's rather like being able to measure the weight and temperature of an invisible object, without being able to see or touch it directly. This situation has led some physicists to wonder whether dark energy represents a fundamental limit to scientific knowledge. Perhaps there are aspects of reality that can only be inferred indirectly, never observed or understood in the same way we understand more familiar phenomena. The universe might contain layers of mystery that can be detected but not fully comprehended, at least not with the kinds of minds and instruments that evolution has provided us. But this possibility, rather than being discouraging, opens up profound questions about the nature of understanding itself. What does it mean to know something? Is there a difference between being able to predict a phenomenon's behavior and truly understanding its essence? Can science provide complete knowledge about reality, or will there always remain aspects of existence that transcend our capacity for comprehension? These philosophical questions become particularly intriguing when we consider consciousness itself. The fact that you're capable of thinking about dark energy, of contemplating forces that operate on cosmic scales, represents something as mysterious as the invisible energy that fills space. How does matter organize itself into patterns capable of self-awareness and cosmic understanding? What is the relationship between the physical processes in your brain and the subjective experience of wondering about the universe? Some theorists have proposed deep connections between consciousness and the fundamental properties of space and time. Perhaps awareness isn't just something that emerges from complex arrangements of matter, but rather a fundamental aspect of reality, woven into the fabric of existence at the deepest level. If this is true, then conscious beings like yourself aren't just passive observers of cosmic evolution, but integral participants in the universe's ongoing attempt to understand itself. This perspective suggests that the questions you're pondering about dark energy aren't separate from dark energy itself, but rather part of the same cosmic story. The universe has evolved over billions of years to produce minds capable of contemplating its own mysteries. The dark energy that drives cosmic expansion has helped create the conditions necessary for complexity, consciousness, and the capacity for wonder that allows you to think about these profound questions. In this view, every thought you have about the nature of space and time participates in the cosmos's journey towards self-understanding. When you wonder about invisible energy, you're not standing outside the universe looking in, but rather serving as one of its organs of perception and comprehension. The boundary between observer and observed dissolves, revealing a reality where consciousness and cosmos are intimately intertwined. This interconnection extends to the very language we use to describe cosmic phenomena. The words dark energy themselves reflect our human need to name and categorize the unknown, to make the invisible somehow accessible to thought and discussion. But perhaps the reality we're trying to describe transcends the limitations of language, existing in ways that can't be fully captured by any combination of words or mathematical symbols. The history of physics is filled with examples of phenomena that initially seemed impossible to understand, but eventually yielded to patient investigation and creative thinking. Quantum mechanics once seemed utterly bizarre and counterintuitive, yet it now forms the foundation for technologies that surround us in daily life. General relativity transformed our understanding of gravity from a force into a curvature of space-time, revealing connections between matter, energy, space, and time that no one had imagined before. Perhaps dark energy will follow a similar trajectory, moving from mystery to understanding through insights that we can't yet anticipate. Future generations might look back on our current confusion about dark energy the way we now view earlier puzzlements about the nature of light or the structure of atoms. What seems impossibly mysterious today might become as familiar and comprehensible as electricity or gravity. Yet, even if we eventually develop a complete theory of dark energy, even if we learn to predict its behavior with perfect accuracy and understand its role in cosmic evolution, the sense of wonder and mystery it evokes might never fully disappear. The universe has a way of revealing new layers of complexity and beauty, just when we think we've grasped its essential nature. Each answered question opens up new avenues of investigation, new mysteries that challenge our understanding in unexpected ways. This endless capacity for surprise and discovery might be one of the universe's most remarkable properties. We inhabit a cosmos that rewards curiosity, that reveals its secrets gradually to those patient and persistent enough to keep asking questions. Dark energy represents just one chapter in an infinitely long book of mysteries, each page revealing new wonders, while hinting at even greater mysteries yet to be explored. The instruments we're building to study dark energy will continue operating long into the future, accumulating ever more precise measurements of cosmic expansion and structure formation. These observations will constrain theories, eliminate some possibilities while opening up others, and gradually narrow the range of viable explanations for the mysterious energy that fills space. But beyond the specific question of dark energy's nature lies a broader truth about the relationship between consciousness and cosmos. We are, quite literally, the universe becoming aware of itself matter and energy arranged in patterns capable of contemplating their own existence and seeking to understand the forces that created them. This capacity for cosmic self-reflection might be as fundamental and mysterious as any force that shapes the expansion of space. As you drift towards sleep tonight, remember that the dark energy surrounding you connects your existence to the largest scales and deepest mysteries of the cosmos. The space between your thoughts participates in the same quantum fluctuations that might drive cosmic expansion. The vacuum in your room shares properties with the vast reaches between galaxies. You are not separate from the cosmic mystery, but embedded within it, made of the same fundamental ingredients that compose stars and space and the invisible energy that shapes everything that exists. In this moment of quiet reflection, you represent something extraordinary in cosmic terms. You are matter that has learned to wonder about itself, energy that has developed the capacity for self-awareness and cosmic understanding. The fact that such awareness can emerge from the dance of particles and fields, that consciousness can arise from the interplay of matter and energy shaped by forces like dark energy, remains one of the most profound mysteries in all of existence. The universe has spent nearly 14 billion years arranging itself to produce moments like this one, where conscious minds can contemplate the invisible forces that govern reality. Dark energy has been patiently shaping space, creating the cosmic environment that allows for the complex chemistry of stars and planets, the intricate processes that lead to life and eventually to awareness itself. Tomorrow, when you wake, that same mysterious energy will continue its ancient work, stretching space and influencing the fate of galaxies across cosmic distances and cosmic time. The mystery will remain, patient and profound, waiting for new insights and discoveries that will illuminate another aspect of the invisible presence that fills our universe. And you will still be part of that ongoing story, carried along by the expansion of space itself, floating through an ocean of dark energy toward whatever revelations await in the magnificent, unknowable future of our endlessly mysterious cosmos. The story of dark energy ultimately brings us full circle to the most fundamental question of all. What does it mean for us to exist in a universe we can barely comprehend? Here we are, conscious beings made of stardust and quantum fields, somehow capable of detecting forces that operate across scales so vast they dwarf our everyday experience. It's rather like being a single cell that has learned to contemplate the entire organism it inhabits, or a drop of water that has developed the ability to study the ocean. This capacity for cosmic understanding represents something almost miraculous when you consider the odds against it. The atoms in your body were forged in the hearts of dying stars billions of years ago. The carbon that forms your DNA, the oxygen you breathe, the calcium in your bones, all of it was scattered into space by stellar explosions and gradually assembled into the complex chemistry that makes life possible. And somehow, through processes we still don't fully understand, this stellar debris has organized itself into patterns capable of self-awareness and wonder. The dark energy that surrounds you right now has been an invisible participant in this entire cosmic story. It helped shape the expansion rate that allowed galaxies to form at just the right pace. It influenced the cosmic environment in which stars could shine long enough to create heavy elements. It contributed to the delicate balance of forces that makes complex structures like planets and life possible. In a very real sense, the mysterious energy that fills empty space is part of the reason you exist at all. This realization transforms dark energy from an abstract scientific concept into something deeply personal and profound. You're not just studying a cosmic phenomenon from a distance. You're exploring the very forces that created the conditions for your existence, the invisible influences that have been shaping reality since long before Earth formed, and will continue their work long after our sun has faded to a cold ember. The questions we're asking about dark energy today represent humanity's latest chapter in an ancient quest to understand our place in the cosmic order. Our ancestors looked up at the night sky and wondered about the lights they saw there. They created myths and stories to explain the motion of celestial bodies, the changing seasons, the relationship between Earth and the heavens above. Each generation has pushed a little further into the mystery, revealing new layers of cosmic complexity while uncovering new questions to ponder. We stand at a remarkable moment in this long journey of discovery. For the first time in human history, we've developed instruments sensitive enough to detect the subtle influence of forces that operate across billions of light years. We can measure how the universe has evolved over most of its history, track the formation and evolution of cosmic structures, and probe the properties of invisible energies that fill the vacuum of space. Yet for all our technological sophistication, for all the precision of our measurements and the elegance of our theories, the deepest questions about dark energy remain tantalizingly out of reach. We can describe its effects with mathematical equations, predict its influence on cosmic evolution, and constrain its properties through careful observation, but we still can't say with certainty what it actually is, or why it exists in exactly the amount we observe. This combination of knowledge and mystery, of precise measurement and profound ignorance, captures something essential about the human condition in the cosmos. We are finite beings with infinite curiosity, temporary arrangements of matter and energy, capable of contemplating forces that operate on scales vastly larger than ourselves. We can glimpse the edges of ultimate truth while remaining forever embedded within the mystery we're trying to solve. Perhaps that's exactly as it should be. A universe that revealed all its secrets easily would be a less interesting place to inhabit. The fact that dark energy remains mysterious, that it challenges our most fundamental assumptions about the nature of space and time, ensures that the cosmos continues to be a place of wonder and discovery. Each answered question reveals new puzzles, each solved mystery points toward deeper layers of cosmic complexity. The future holds extraordinary possibilities for our understanding of dark energy and the broader cosmic story it represents. New telescopes will survey ever larger volumes of space with unprecedented precision. Advanced detectors will probe the properties of the quantum vacuum with exquisite sensitivity. Theoretical physicists will develop new mathematical frameworks that might finally bridge the gap between quantum mechanics and general relativity. But whatever we discover, however much our understanding advances, the sense of wonder and mystery that dark energy evokes will likely persist. The universe seems designed to reward curiosity while maintaining an endless capacity for surprise. Just when we think we've grasped its essential nature, it reveals new layers of complexity that challenge our assumptions and force us to think in entirely new ways. This ongoing dance between knowledge and mystery, between understanding and wonder, might be one of the most beautiful aspects of conscious existence in our cosmos. We get to participate in the universe's attempt to understand itself, to serve as temporary focal points where matter and energy achieve self-awareness and begin to comprehend the forces that shape them. The dark energy that fills the space around you right now connects you to this grand cosmic story in the most intimate way possible. It's not separate from your existence, but woven into the very fabric of the reality you inhabit. The quantum fluctuations that might give rise to cosmic acceleration occur in the vacuum between the atoms in your body. The mysterious pressure that drives galactic recession operates in the space between your thoughts. You are, quite literally, floating in an ocean of invisible energy that we're only beginning to understand. This energy has been shaping the cosmos since the earliest moments after the Big Bang, creating the conditions that allowed for the formation of galaxies, stars, planets, and eventually life itself. It represents one of the deepest mysteries we've ever encountered, yet it's as close to you as your own breath. As we reach the end of our gentle journey through the mystery of dark energy, remember that this isn't really an ending, but rather a pause in an ongoing story of discovery. The questions we've explored tonight will continue to challenge and inspire future generations of cosmic explorers. The telescopes being built today will reveal new aspects of dark energy's behavior. The theories being developed in universities around the world might finally unlock the secret of what fills the vacuum of space. But even as our scientific understanding advances, the fundamental sense of wonder that dark energy evokes will likely endure. We are conscious beings in a cosmos dominated by invisible forces, temporary patterns of matter and energy capable of contemplating the very mechanisms that govern our existence. This capacity for cosmic self-reflection might be as mysterious and remarkable as any force that shapes the expansion of space. So as you drift towards sleep tonight, carried gently along by the universe's ongoing expansion, remember that you're part of something magnificent and mysterious. The dark energy that surrounds you connects your existence to the largest scales and deepest questions in all of physics. You are not separate from the cosmic mystery but embedded within it, a conscious participant in the universe's journey towards self-understanding. The space around you pulses with quantum activity that might drive the expansion of everything that exists. The vacuum between your atoms participates in the same invisible dance that influences the motion of galaxies across billions of light years. You are swimming in an ocean of mystery that extends from the smallest scales to the cosmic horizon, from the quantum realm to the vast reaches of intergalactic space. In this moment of quiet reflection, as your thoughts slow and your breathing deepens, you represent something extraordinary in cosmic terms. You are matter that has learned to wonder about itself, energy that has developed the capacity for curiosity and understanding. The fact that such awareness can emerge from the interplay of particles and fields, shaped by forces like dark energy over billions of years, remains one of the most profound mysteries in all of existence. The universe has been preparing for this moment for nearly 14 billion years, arranging matter and energy in increasingly complex patterns that eventually gave rise to stars, planets, life, and consciousness. Dark energy has been a patient participant in this cosmic evolution, helping to create the stable environment necessary for complexity to emerge and flourish. Tomorrow, when you wake, that same mysterious energy will continue its ancient work, stretching space and shaping the fate of everything that exists. The mystery will remain deep and profound, waiting for new insights that will illuminate another aspect of the invisible presence that fills our cosmos. And you will still be part of that ongoing story, floating through an ocean of dark energy toward whatever revelations await in the magnificent, unknowable future of our endlessly surprising universe. Until we meet again for another gentle journey through the wonders of science, sleep well, fellow traveler. May your dreams be filled with the quiet beauty of cosmic mysteries, and may you rest peacefully knowing that you're cradled in the invisible embrace of forces that connect you to the deepest truths of existence itself. The dark energy that fills the universe is not just around you, but within you, part of the same cosmic story that includes your thoughts, your wonder, and your capacity to contemplate the magnificent mystery of being alive in such an extraordinary cosmos.